In this video, we continue our discussion of row reduction and echelon forms with a discussion of the relationship between echelon forms of the augmented matrix of a linear system and the solutions of that linear system. So let's say we have a linear system like this. If I want to come up with the augmented matrix for that system like this, it's actually pretty easy. All you do is you make sure that your equations are arranged in this way with all of your x sub 1s sort of stacked vertically, the same thing with your x sub 2s and the same thing with your x sub 3s. And then you list the coefficients of x sub 1, x sub 2, and x sub 3 in each row. So we've got a 1, 2, and 3 there. Here we have a 4, 5, and 6. Here we have a 6, 7, and an 8. And then this would be, just by itself, without that column, the coefficient matrix of that linear system. If then we take that coefficient matrix and then we add on this extra column that contains the entries or the numbers on the right-hand side of each of those equations, we get what's called the augmented matrix of that system. Now, when we apply the row reduction algorithm to this augmented matrix of this system, in the last video, we did that. It was this augmented matrix that we row reduced using our algorithm. And we got this as our reduced row echelon form of the augmented matrix. Now, just as a review, we know that this is an echelon form because we see that stair-step pattern like this. We've got a leading entry right here in this first row and first column. And then as we look at the matrix from left to right, the pivots sort of go down. They go down and to the right as we move across the matrix. So that's that echelon pattern. The leading entry in the second row is to the right of the leading entry in the first. And that pattern would continue to hold, but I guess there are only 4 columns here. And there are only 2 pivot positions, 2 non-zero, or excuse me, 2 pivot columns here. So that's what makes it a row echelon form of a matrix. We don't have, or we have a row of zeros, and that row of zeros is below all of the other rows. And the leading entry in each of these rows follows that pattern where the leading entry in the second row is to the right of the leading entry in the first. And then the leading entry in the third row, well, it turns out that the third row doesn't have a leading entry. So that makes that row echelon form. It's reduced row echelon form because in addition, our pivots are equal to 1. So we've got leading 1s there rather than other numbers. And in each column, in each of those pivot columns, the 1s are the only non-zero entries. The other entries are zeros. So this is the reduced row echelon form of this augmented matrix. And this is the process that we followed last time in order to get it. And this is the process in much more detail. But I want you to remember that whenever you're using this row reduction algorithm to take a matrix and write it in either row echelon form or reduced row echelon form, what you're doing is you are sort of manipulating the coefficients and the right-hand side of each of those equations in much the same way that you would if you were just multiplying equations by constants and adding them together. So if I took this first equation and I multiplied it by -4, and then I added that result to the second equation, what I would get is an equation with the coefficients and right-hand side listed right here. So this row resulted from taking that first row and multiplying it by -4 and adding it to the second row. Well, that corresponds to taking this first equation and multiplying it by -4 and adding it to the second equation. When we get this row, we can interpret that row as an equation. This tells me that -3 times x sub 2 minus 6 times x sub 3 is equal to -9. And then if I take that equation and I divide it by -3, I get this equation that says that at 1 times x sub 2 plus 2 times x sub 3 is equal to 3. So every time we applied an elementary row operation to this matrix to get a row equivalent matrix, It's just as if we had manipulated those original equations in that way. So the equations and the rows are playing the same role here. They don't always have to. This matrix doesn't necessarily have to represent the augmented matrix of a linear system. But if the matrix does represent the augmented matrix of a linear system, by row reducing, eventually we get to a matrix that looks, something like this. And this corresponds to a system of equations as well. So if I take this reduced row echelon form of the augmented matrix of this system, well, that corresponds to what we call the reduced system. The reduced system of the linear system is a new system of equations. And this system of equations is given by the entries in the reduced row echelon form of the augmented matrix. So this first row tells me that 1 times x sub 1 plus 0 times x sub 2 plus -1 times x sub 3 equals -2. And the second row tells me that 0 times x sub 1 plus 1 times x sub 2 plus 2 times x sub 3 equals 3. And the last row just tells me that 0 times x sub 1 plus 0 times x sub 2 plus 0 times x sub 3 equals 0. But we already knew that 0 equaled 0, so we don't have to write that down. So this corresponds to this, and I actually wouldn't call this the reduced system. Normally, we don't write all of those 0 entries out. I would call this the reduced system. Got x sub 1 minus x sub 3 equals -2, and x sub 2 plus 2 times x sub 3 equals 3. That is the reduced system of the original system of equations. And again, it just came from taking that reduced row echelon form and writing it as a corresponding system of equations. Now, when I'm looking at this reduced row echelon form, this is a pivot column. And this is a pivot column because they contain pivots. This column corresponds to the coefficients. This first column corresponds to the coefficients of the variable x sub 1, and the second column corresponds to the coefficients of x sub 2. Since we're in reduced row echelon form here, there's only one row that contains an x sub 1. It's the first row. And there's only one row that contains the variable x, or actually, let me say that again. There's only one row here that has a non-zero coefficient for x sub 1, and that's the first row. And there's only one row here, that's the second row, that tells us, that corresponds to an equation containing x sub 2. So x sub 1 and x sub 2 only appear in one equation each. This appears in the first equation. X sub 2 appears in the second equation. This column is not a pivot column because it doesn't contain the leading entry of any row. But this contains coefficients of x sub 3. Notice that x sub 3 appears in the first equation and the second equation because of those two numbers there, which correspond to those two terms there in those two linear equations. We can use this to define some new terms. Basic variables are variables in pivot columns. And free variables are variables that are not represented by pivot columns. or let's say they're not associated with a pivot column. So in this example, x sub 1 and x sub 2 are basic variables. And x sub 3 is what we call a free variable. Now, if we want to write the solution set of this system of equations explicitly, we can take this reduced system and solve it for the free variable, or the basic variables x sub 1 and x sub 2 in terms of any free variables. So let's write that down. We'll say if the solution set, or if the system of equations is consistent, meaning that it has at least one solution. Then the solution set may be completely described by solving the reduced system for the basic variables, and those basic variables each appear in one equation only. So this one equation contains x1 and this one equation contains x2. We're going to solve for those in terms of the free variables. So if I add x sub 3 to both sides, in this equation I have x sub 1 is equal to negative 2 plus x sub 3. And if I subtract 2 times x sub 3 from both sides, I have x sub 2 is equal to 3 minus 2 times x sub 3. So this is, oh, and then x sub 3 is free to be anything. So we'll just call that free there. This is an explicit description of all solutions of the original system of equations. That's what we call the general solution of the original linear system. Now, it's actually not necessary to solve the system, this reduced system for x sub 1 and x sub 2 in terms of x sub 3. We could solve this system of two equations with three unknowns for x sub 1 and x sub 3 in terms of x sub 2, or x sub 2 and x sub 3 in terms of x sub 1. All of those possibilities are possible. Since we have two equations and we have three unknowns, one of the variables can be anything, and the values of the other two variables are determined by these equations. Now, when we tend to do that in this class, we always choose to solve for the basic variables in terms of the free variables. So we get x sub 1 and x sub 2, those in the pivot, or those variables that correspond to pivot columns by themselves, rather than solving for x sub 1 and x sub 3 in terms of x sub 2, for example. But that is just a choice that we're making, and that's a convention that we follow, but it's not necessary to follow that convention. But this is the general solution of the linear system. And, excuse me. This is closely related to what we call the parametric description of the solution set. This is a description of the solution set in which the free variables act as parameters. Now, it's actually not necessary that the free variable act as a parameter. We could, again, we just choose to let the free variable act as a parameter. And of course, this is only possible. It's only possible to come up with these if the solution set is non-empty. Or in other words, the system is consistent. So those are just multiple ways of saying the same thing. Saying the system is consistent is the same as saying that the solution set is non-empty, which is the same as saying that the system of equations, the original system of equations, has at least one solution. Now, of course, if the solution set is empty, meaning the solution or the system is inconsistent, then it doesn't make sense to talk about a general solution or a parametric description of the solution set because there is no solution set. The solution set has nothing in it. It's empty. Okay, so I think we see now how the echelon form of the augmented matrix of a linear system can tell us something about the solutions of those linear systems, or of that linear system. If we take the linear system of equations and we write it as an augmented matrix, and then we row reduce that augmented matrix until it's in this form. If we have a situation like this, where we end up with a free variable, or more than one free variable, then we end up with something like this, and then the solution, or the general solution, or a parametric description would look something like this. And that means we have infinitely many solutions. So if x sub 3 is equal to 0, that's fine as long as x sub 1 is equal to 2 and x sub 2 is equal to 3. The point x sub 1, x sub 2, x sub 3 equals -2, 3, 0 is a solution of that system. But we could have just as easily chosen x sub 3 to be, let's say, 1. If x sub 3 is 1, then x sub 1 is -2 plus 1, which is -1, and x sub 2 is 3 minus 2, which is 1. So that's a solution of our system. So it just turns out that if x sub 3 is any variable or any value, often when we're talking about parametric representations, we let one of those, that free variable be t. Well, then x sub 1 is just going to be -2 plus t, and x sub 2 is going to be 3 minus 2t. That's how we typically write it, but in this case, we're just leaving it in terms of the variable x sub 3. This is a point in the solution set. This is a point in the solution set. And this is one way of describing all of the points in the solution set where t can take on any real number. So if you're in a scenario like this, where you have a free variable. If you have at least one free variable, then you have infinitely many solutions, and that set of infinitely many solutions can be described parametrically. I'm getting ahead of myself a little bit. I'm starting to answer the existence and uniqueness questions. So here they are. Here's the first question. And this is about consistency. And does the linear system have a solution? Here's the idea. If the reduced row echelon form of the augmented matrix of the system contains a row of this form, which has zeros in all of the columns except for the last one, where that last column gives us a value that's not equal to 0, then the linear system does not have a solution. The linear system has no solutions, which means that we say the system is inconsistent. Which means, or in other words, we can say that the solution set is the empty set. Or if S represents a solution set, we'll say S is equal to the empty set, like that. Now, if we are in a case where we have consistency, if you're trying to decide whether you have a single solution or infinitely many solutions, that depends on the number of free variables. So we'll say if the reduced row echelon form of the augmented matrix let's say indicates that the reduced system has free variables, let's say has at least one free variable, then there are infinitely many solutions corresponding to different values of that free variable or variables. Now, if the reduced row echelon form of the augmented matrix indicates that the reduced system has no free variables, if all of the variables are basic variables, then in that case, we have one and only one solution. And it actually doesn't have to be reduced row echelon form. All we would need is row echelon form in order to determine this, because the number of pivots is exactly the same. The number and the position of the pivots, positions of pivots are exactly the same in the reduced row echelon form and the row echelon form. Now, if you're a student and you're saying, but Miss Townsend, what do you mean by this? How can I tell whether that reduced system has at least one free variable? You need to look at the number of equations that you started with, and then the number of equations that you ended up with. So if we started with 3 equations and we ended up with 2 equations, that might tell us something. Also, we want to look at the number of pivot columns that we have relative to the number of columns that we have total. If we have, let's say, m columns, if the first m minus 1 of them are pivot columns, if all of these columns at the beginning are pivot columns, and we have enough equations for each variable. So we have 3 equations with 3 unknowns, and then each of those 3 unknowns is specified by an equation as indicated by a pivot in that column. Then we have one solution. I guess I'm not actually making this any clearer, am I? Here's the idea. If we have n equations and n unknowns, and we don't always have that, so the same number of rows or number of unknowns and equations. If that's true, and we have n pivot columns, and the system is consistent, so the pivot columns are the first n columns and not that last one, then we have one and only one solution. So the solution exists and it's unique. Now, if we have a different number of equations and unknowns, if we don't have enough equations for all of the unknowns, then we'll have at least one free variable. But that's not the only way that we get free variables. We started, remember with this example, we started with 3 equations and 3 unknowns, and it turned out that after row reducing, we ended up with 2 equations and 2 unknowns. That third variable happened to be free. So that will sometimes happen as you're row reducing. That means that we're in this case. If you just look at that matrix, I think that you can tell that this is a pivot column, this is a pivot column, this does not contain any pivots. And so if you have a column corresponding to a variable that does not contain pivots, well, that's a free variable. And that tells you, if you have a free variable like that, then you have infinitely many solutions. Now, just as an example for this one, and I'm not going to go through the entire thing with you, but I did want to give you at least one concrete example. I actually may have lost that example as I was taking these notes. Yeah, I don't know where I put it. And that's okay. If you have a row that looks like this with a bunch of zeros here and a non-zero number here, just know that that corresponds to an equation that could never make sense. This is saying 0 times x1 plus 0 times x2 all the way through plus 0 times x sub n equals b. So that's a sum of n zeros, which is 0, and you're saying 0 equals b, and b is not 0, that can never be true. If you end up with something like that, the linear system does not have a solution. Otherwise, we have a solution, and the number of solutions depends on whether or not we have free variables. If we have a pivot column for every variable, and that will happen if we have the same number of equations and the same number of unknowns, or maybe more equations than we had unknowns, and then a pivot column for each of those unknowns, then we have one solution. Okay, I think I'm just going to stop there. I think I'm talking too much. I'll see you in the next video, and we'll talk a little bit more about vectors and how vectors relate to matrices and equations.